Welcome, dear listener. Tonight, we embark on a peaceful journey through the wonders of our home planet. As you settle into your comfortable position, allow your breathing to slow and your muscles to relax. Let these gentle facts about Earth carry you into restful slumber. There is nothing you need to do, nowhere you need to be. Simply listen and drift. Take a slow, deep breath in, and release it gently. Feel the weight of your body sinking into the surface beneath you. Your bed is like a small piece of Earth itself, supporting you, cradling you, as our planet has cradled countless generations before. Let us begin our exploration of this extraordinary world we call home. Our planet Earth formed approximately 4.5 billion years ago, emerging from a swirling disk of gas and dust that surrounded our young sun. In those earliest days, countless small rocky bodies collided and merged together, gradually building the world we now call home. The heat from these collisions, combined with the decay of radioactive elements, caused the early Earth to become molten, allowing heavier materials like iron and nickel to sink toward the center while lighter rocks floated toward the surface. Picture, if you will, that ancient time when our solar system was young. Where Earth now orbits, there was only a cloud of debris, spinning slowly around a newly ignited star. Gravity drew these particles together, piece by piece, over millions of years. First pebbles, then boulders, then mountains of rock colliding in the darkness of space. This process, called accretion, built our world grain by grain, impact by impact. If we were to compress all of Earth's history into a single 24-hour day, human civilization would appear only in the final second before midnight. The dinosaurs would have gone extinct around 11:40 in the evening. Complex life would have emerged around 9 in the evening. And for almost the entire day, from midnight until about 5 in the afternoon, Earth would have been inhabited only by microscopic organisms. This perspective reminds us how ancient and patient our planet truly is, how many transformations it has witnessed, how many forms of life it has cradled through the ages. The oldest known minerals on Earth are tiny zircon crystals found in the Jack Hills region of Western Australia, dated to approximately 4.4 billion years old. These microscopic time capsules, smaller than a grain of sand, have survived through almost the entirety of Earth's existence, witnessing the formation of the first oceans, the emergence of life, and the slow dance of continents across the globe. Within their crystalline structure, they preserve chemical signatures that tell us the early Earth had liquid water much sooner than scientists once believed. The early Earth was a violent place, constantly bombarded by asteroids and comets in a period known as the Late Heavy Bombardment. This cosmic rain of debris continued for hundreds of millions of years, perhaps delivering some of the water that now fills our oceans, and possibly even the organic compounds that would eventually give rise to life. The Moon still bears the scars of this bombardment in its heavily cratered surface. Earth continues to cool very gradually from its formation. The temperature at the very center of our planet reaches approximately 10,800 degrees Fahrenheit, which is actually hotter than the surface of the sun. This tremendous heat drives the movements of our planet's interior and powers the magnetic field that protects us from harmful solar radiation. The Earth loses heat at a rate of about 47 terawatts, roughly 3 times humanity's total power consumption. The Moon, our constant celestial companion, likely formed when a Mars-sized object called Theia collided with the early Earth about 4.5 billion years ago. This cataclysmic impact was so violent that it vaporized much of both bodies, sending a massive cloud of debris into orbit around the wounded Earth. This debris gradually coalesced into the Moon we see tonight, taking perhaps as little as 100 years to form. In those early days, the Moon was much closer to Earth, perhaps only about 15,000 miles away, and appeared far larger in the sky. The days were much shorter then, lasting only about 6 hours, because Earth was spinning much faster. The Moon has been slowly drifting away from Earth ever since, stealing a tiny bit of our planet's rotational energy through tidal interactions. Each year, the Moon moves about 1.5 inches farther from us. In the distant future, billions of years from now, the Moon will appear smaller in our sky, and total solar eclipses will become impossible because the Moon will no longer be large enough to fully cover the sun. Let your thoughts drift now to the structure of our planet, layers upon layers of rock and metal extending thousands of miles beneath your resting body. As you lie still, know that far below you, the Earth is anything but still. Currents of molten rock flow slowly through the mantle. The liquid outer core churns and swirls. Our planet is alive with movement we cannot see or feel. Earth is composed of 4 main layers, each with its own character and composition, like a great cosmic onion of rock and metal. The innermost layer, the inner core, is a solid ball of iron and nickel approximately 760 miles in diameter, roughly the size of the moon. Despite temperatures exceeding those found on the surface of the sun, this core remains solid because of the immense pressure bearing down upon it from all the material above. The pressure at the center of the Earth is about 360 gigapascals, more than 3 million times the atmospheric pressure at sea level. Scientists believe the inner core is crystalline, with iron atoms arranged in a regular lattice structure. There is evidence that the inner core may actually be rotating slightly faster than the rest of the planet, completing an extra rotation roughly every 1,000 years. Some research suggests the inner core has its own internal structure, with an innermost inner core that has crystals aligned in a different direction than the surrounding material. Surrounding the inner core is the outer core, a layer of liquid iron and nickel about 1,400 miles thick. The temperature of this molten metal ranges from about 7,200 degrees Fahrenheit near the mantle to nearly 11,000 degrees near the inner core. The movement of this electrically conductive fluid generates Earth's magnetic field through a process called the geodynamo, similar to how a bicycle dynamo generates electricity through motion. The outer core flows in complex convection patterns driven by the cooling of the core and the slow growth of the solid inner core. As iron crystallizes onto the inner core, it releases heat and lighter elements, driving convection currents that twist and turn through the liquid metal. These currents, interacting with Earth's rotation, create the self-sustaining magnetic dynamo that has protected our planet for billions of years. Above the outer core lies the mantle, the thickest layer of Earth, extending about 1,800 miles from the core to the crust. The mantle makes up about 84% of Earth's total volume. Though we often think of rock as solid and unchanging, the mantle behaves almost like an extremely thick fluid over millions of years, flowing slowly in great convection currents driven by the heat from below. This flow is incredibly slow by human standards, perhaps only a few centimeters per year, but over geological time, it has reshaped the surface of our planet countless times. The mantle is composed primarily of silicate rocks rich in iron and magnesium. The most common mineral in Earth's mantle is bridgemanite, which makes up about 38% of Earth's total volume. This mineral was only first observed in its natural state in 2014, found in a meteorite, because the extreme pressures needed to form it make it impossible to bring samples to the surface without the mineral transforming into other forms. The boundary between the mantle and the crust is called the Mohorovičić discontinuity, or MOHO for short, named after the Croatian seismologist who discovered it in 1909. Below this boundary, seismic waves suddenly speed up, indicating a change in rock composition and density. The MOHO lies at different depths beneath the oceans and continents. The crust upon which we live is remarkably thin compared to these deeper layers. Oceanic crust, found beneath the seas, averages only about 4 miles in thickness and is composed primarily of dense basalt rock. Continental crust is somewhat thicker, ranging from about 20 to 30 miles deep, and is made of lighter granite and other rocks. If Earth were the size of an apple, the crust would be thinner than the apple's skin. The oceanic crust is constantly being created and destroyed. At mid-ocean ridges, new crust forms as magma rises from the mantle and solidifies. At subduction zones, old crust sinks back into the mantle, completing a cycle that takes about 200 million years. The oldest oceanic crust on Earth is only about 200 million years old, found in the eastern Mediterranean. In contrast, continental crust is more permanent because its lower density makes it resistant to subduction. The oldest known continental crust is about 4 billion years old, found in the Canadian Shield. Earth is composed primarily of iron, which makes up about 32% of the planet's total mass. Oxygen is the second most abundant element at about 30%, followed by silicon at about 15% and magnesium at about 14%. These four elements alone account for more than 90% of our planet's composition. Despite its abundance on the surface, oxygen is actually the most common element in the Earth's crust, making up nearly half of its mass, mostly bound in silicate minerals. Every element heavier than hydrogen and helium was forged in the hearts of ancient stars or in the violent explosions of supernovae. The gold in wedding rings, the calcium in bones, the iron in blood, all of these atoms were created in stellar furnaces long before our solar system existed. In this very real sense, we are all made of stardust, as is our planet itself. As you breathe slowly and deeply, consider the thin envelope of gases that surrounds our planet, the atmosphere that gives us the air we breathe and paints our skies with color. With each breath you take, molecules of oxygen enter your lungs, molecules that may have been breathed by countless creatures before you, recycled endlessly through the great cycles of life and atmosphere. This layer of gases extends about 300 miles above the surface, though it becomes increasingly thin with altitude, gradually fading into the vacuum of space. The atmosphere contains approximately 5 quadrillion tons of air, a number so large it defies easy comprehension. Yet this seemingly vast quantity is actually quite fragile when compared to the solid Earth below. If you could compress the entire atmosphere to the density of water, it would form a layer only about 33 feet deep around the planet. The atmosphere is divided into 5 main layers, each with its own characteristics and wonders. The troposphere, where we live and where weather occurs, extends from the surface to about 7 miles high at the poles and about 11 miles high at the equator. This layer contains about 75% of all the atmosphere's mass and nearly all of its water vapor. The troposphere is where clouds form, where rain falls, where winds blow. Temperature generally decreases with altitude in this layer, dropping about 3.5 degrees Fahrenheit for every 1,000 feet you climb. The word troposphere comes from the Greek word tropos, meaning turning or mixing. This layer is indeed well mixed, with air constantly circulating through convection currents powered by the sun's heat. The boundary at the top of the troposphere, called the tropopause, acts as a lid that largely prevents water vapor from entering the stratosphere above. Above the troposphere lies the stratosphere, extending from about 7 to 31 miles above the surface. This layer is home to the ozone layer, a region where ozone molecules, each made of 3 oxygen atoms, absorb much of the sun's harmful ultraviolet radiation. Commercial aircraft often cruise in the lower stratosphere, where the air is calm and clear, free from the turbulence and weather of the troposphere below. The ozone layer, though critical to life on Earth, is remarkably thin. If all the ozone in the atmosphere were compressed to sea level pressure, it would form a layer only about 3 millimeters thick, roughly the thickness of 2 stacked coins. Yet this thin veil of ozone protects every living thing on Earth's surface from the sun's damaging ultraviolet rays, which can cause skin cancer, cataracts, and harm to plants and marine ecosystems. Unlike the troposphere, temperature increases with altitude in the stratosphere because ozone absorbs ultraviolet light and converts it to heat. This temperature inversion makes the stratosphere very stable, with little vertical mixing. Air in the stratosphere can remain there for years, which is why pollutants that reach this layer, like the chlorofluorocarbons that damage the ozone layer, can persist for so long. The mesosphere extends from about 31 to 53 miles above the surface. This is where most meteors burn up as they enter Earth's atmosphere, creating the shooting stars we sometimes see on clear nights. About 40,000 tons of cosmic material enters the atmosphere each year, most of it vaporizing in the mesosphere, leaving behind only a fine dust of particles that slowly drifts down through the atmosphere. Temperatures in the mesosphere can drop to minus 130 degrees Fahrenheit, making it the coldest layer of the atmosphere. Despite being above most of the atmosphere, the mesosphere is difficult to study because it is too high for weather balloons and too low for most satellites. Scientists sometimes call it the ignorosphere because of how little we know about it compared to other layers. The thermosphere and exosphere form the outermost reaches of our atmosphere, gradually transitioning into the vacuum of space. The thermosphere extends from about 53 to 370 miles above the surface. In this layer, temperatures can soar above 3,600 degrees Fahrenheit, though the air is so thin that a thermometer would actually register extreme cold. This is because temperature, in a physics sense, is related to how fast molecules are moving, and the sparse molecules in the thermosphere move very fast when energized by solar radiation. But with so few molecules present, there is very little heat to transfer to any object up there. The International Space Station orbits within the thermosphere, about 250 miles above the surface. Astronauts there experience sunrise and sunset 16 times per day as they circle the Earth every 90 minutes. From this altitude, the thin blue line of the atmosphere is clearly visible against the blackness of space, a fragile ribbon of air that makes our planet habitable. The exosphere, the outermost layer, begins at about 370 miles and gradually fades into interplanetary space. Here, the air is so thin that molecules can travel hundreds of miles without colliding with another molecule. The exosphere contains mainly hydrogen and helium, the lightest gases, which slowly escape into space. The sky appears blue during the day because of a phenomenon called Rayleigh scattering. Sunlight contains all colors of the spectrum, but blue light has a shorter wavelength and is scattered more easily by the tiny molecules of nitrogen and oxygen in our atmosphere. When sunlight enters the atmosphere, the blue component is scattered in all directions, bouncing from molecule to molecule like a pinball. This scattered blue light reaches our eyes from all directions, painting the sky in shades of azure. Interestingly, if our eyes were more sensitive to violet light, the sky would appear violet rather than blue, since violet has an even shorter wavelength and is scattered even more. At sunrise and sunset, sunlight must travel through more of the atmosphere to reach our eyes. The blue light is scattered away before it can reach us, leaving the longer wavelengths of red and orange to color the sky in those warm, peaceful tones that signal the transition between day and night. Dust, pollution, and volcanic ash in the atmosphere can enhance these colors, creating particularly vivid sunsets. Water, that most essential substance for life as we know it, covers approximately 71% of Earth's surface. From space, our planet appears as a blue marble, dominated by the vast expanses of the oceans. Our planet holds about 326 million trillion gallons of water, a number so vast it defies easy comprehension. Yet of all this water, only about 2.5% is freshwater, and most of that is locked away in glaciers and ice caps or hidden deep underground. The origin of Earth's water remains somewhat mysterious. Some water may have been present in the rocks that formed our planet, released through volcanic activity. Additional water was likely delivered by comets and water-rich asteroids that bombarded the early Earth. Whatever its source, water has been cycling through our planet systems for billions of years, evaporating, condensing, flowing, and sustaining life through countless generations. The oceans contain about 97% of all water on Earth. These vast bodies of water regulate our planet's climate, absorbing heat from the sun and distributing it around the globe through great ocean currents. The ocean has absorbed about 90% of the excess heat caused by human activities in recent decades, moderating the warming of the atmosphere. Without the ocean's enormous capacity to absorb heat, the planet would be warming much more rapidly. The oceans also absorb about 30% of the carbon dioxide released by human activities, which has made the ocean about 30% more acidic than it was before the Industrial Revolution. This acidification poses challenges for shell-building organisms like corals, oysters, and many species of plankton. Ocean currents form a global conveyor belt that circulates water around the planet over centuries. Warm surface currents carry heat from the tropics toward the poles, while cold, dense water sinks in polar regions and flows along the ocean floor back toward the equator. This circulation, called thermohaline circulation, helps regulate global climate and distributes heat more evenly around the planet. A single drop of water may take about 1,000 years to complete this global journey. The deepest point in the ocean is the Challenger Deep, located in the Mariana Trench in the western Pacific Ocean. This abyss reaches a depth of approximately 36,000 feet, deep enough to submerge Mount Everest with more than a mile of water to spare. The pressure at this depth is over 1,000 times greater than at the surface, about 16,000 pounds per square inch. Yet life persists even in these crushing depths. Strange creatures adapted to the darkness and pressure have been found in the deepest trenches, including shrimp-like amphipods and fish with translucent, gelatinous bodies. Only 3 people have ever reached the bottom of the Challenger Deep. In 1960, Jacques Piccard and Don Walsh descended in the bathyscaphe Trieste. In 2012, filmmaker James Cameron made the journey solo in the Deep-Sea Challenger. More people have walked on the moon than have visited the deepest point on Earth. Ocean water is salty because rivers continuously carry dissolved minerals from the land to the sea. Rainwater, slightly acidic from absorbing carbon dioxide, dissolves minerals from rocks as it flows over land. Rivers carry these dissolved minerals to the ocean, where the water evaporates but the minerals remain, concentrating over time. Over billions of years, these minerals have accumulated, giving seawater an average salinity of about 3.5%. If all the salt in the ocean could be removed and spread evenly over the Earth's land surface, it would form a layer more than 500 feet thick. The ocean is home to an estimated 228,450 known species, but scientists believe the true number may be closer to 2 million. New species are discovered regularly in the depths, reminding us how much remains unknown about our own planet. The deep sea is the largest habitat on Earth, yet it remains largely unexplored. We have better maps of the Moon and Mars than we do of our own ocean floor. The average depth of the ocean is about 12,100 feet. If you were to drain all the water from the oceans, the resulting basin would reveal vast plains, mountain ranges taller than the Himalayas, canyons deeper than the Grand Canyon, and volcanic ridges stretching across the globe. The Mid-Atlantic Ridge, running down the center of the Atlantic Ocean, is the longest mountain range on Earth, stretching about 10,000 miles. Water is one of the very few substances that expands when it freezes, which is why ice floats. This seemingly simple property has profound implications for life on Earth. If ice sank, lakes and oceans would freeze from the bottom up, making it far more difficult for aquatic life to survive cold winters. Instead, ice forms a protective layer on the surface, insulating the liquid water below and allowing fish and other creatures to survive even the harshest winters. Water has an unusually high specific heat capacity, meaning it can absorb a large amount of heat without changing temperature significantly. This property helps moderate Earth's climate, as the oceans absorb heat during the day and release it at night, reducing temperature extremes. Coastal areas tend to have milder climates than inland regions because of this moderating effect. The water you drink today has been recycled countless times through Earth's water cycle. The same water molecules have fallen as rain over dinosaurs, flowed through ancient rivers, and evaporated from prehistoric seas. In a very real sense, you're connected to every era of Earth's history through the water that sustains you. The water in your glass may once have been part of a glacier during the last ice age, or it may have been drunk by a thirsty mammoth on the ancient steppes of Siberia. Let your mind wander now to the great mountains of the world, those majestic peaks that rise toward the heavens. Picture the sharp, snow-capped summits, the steep slopes covered in ancient rock, the valleys carved by glaciers over thousands of years. Mountains inspire a sense of permanence and timelessness, yet even these mighty formations are constantly changing, rising and eroding, built up and worn down by the patient forces of geology. Mountains form through the slow but inexorable forces of plate tectonics, as sections of Earth's crust collide, fold, and thrust upward over millions of years. Some mountains form when oceanic plates dive beneath continental plates, causing the overlying crust to buckle and rise. Others form where 2 continental plates collide head-on, crumpling like the hoods of 2 cars in a slow-motion collision. Still others form from volcanic activity, as molten rock erupts from the depths and builds layer upon layer of lava and ash. Mount Everest, the tallest mountain above sea level, reaches a height of 29,032 feet above the waves. This mighty peak grows approximately 4 millimeters taller each year as the Indian subcontinent continues to push northward into Asia, a journey that began over 50 million years ago and continues to this day. The rocks at Everest's summit were once at the bottom of an ancient sea called the Tethys Ocean, containing fossils of marine creatures like crinoids, trilobites, and ammonites that lived hundreds of millions of years ago. The summit of Everest is so high that climbers entering the death zone above 26,000 feet experience air pressure only about one-third that at sea level. The oxygen content is so low that most climbers require supplemental oxygen to survive. At the very top, climbers are breathing air that contains only about the same amount of oxygen as they would find at sea level on an airplane pressurized to a comfortable cabin altitude. However, if we measure from base to summit, the tallest mountain on Earth is Mauna Kea in Hawaii. While its summit rises only 13,796 feet above sea level, Mauna Kea extends another 19,700 feet below the ocean's surface, giving it a total height of approximately 33,500 feet, more than 4,000 feet taller than Everest measured this way. Mauna Kea is a shield volcano, built by countless lava flows over hundreds of thousands of years. The highest mountain measured from the center of the Earth is Mount Chimborazo in Ecuador. Because Earth bulges at the equator due to its rotation, Chimborazo's summit, though only about 20,700 feet above sea level, is farther from the Earth's center than any other point on the surface. From the center of the Earth, Chimborazo's peak is about 1.25 miles farther than the summit of Everest. The longest mountain range on Earth is not found on any continent but beneath the sea. The mid-ocean ridge system stretches for approximately 40,000 miles around the globe, winding through every ocean like the seams on a baseball. At these underwater ridges, new oceanic crust is continuously created as magma rises from the mantle and solidifies. The ridges mark the boundaries where tectonic plates are pulling apart, and the seafloor spreads at rates of a few centimeters per year. The Himalayas, the world's highest mountain range, began forming about 50 million years ago when the Indian subcontinent collided with Asia. Before this collision, India was an island continent drifting northward across what is now the Indian Ocean, traveling at the geologically rapid pace of about 6 inches per year. The collision is still ongoing, which is why the Himalayas continue to grow. The range contains all 14 of the world's peaks above 8,000 meters, including Everest, K2, Kanchenjunga, and Lhotse. The Andes, the longest continental mountain range, stretches about 4,500 miles along the western coast of South America. This range includes the highest peak in the Western Hemisphere, Aconcagua, which rises to 22,837 feet in Argentina. The Andes formed primarily through the subduction of the Nazca Plate beneath the South American Plate, a process that also fuels the many volcanoes that dot the range. The Grand Canyon, carved by the Colorado River over millions of years, exposes nearly 2 billion years of Earth's geological history in its colorful layers of rock. Standing at the rim and looking down through these layers is like reading a book written in stone, each chapter representing a different era of our planet's past. The canyon is about 1 mile deep, up to 18 miles wide, and about 277 miles long. The river continues to deepen the canyon today, cutting through the rock at a rate of about 1 foot every 1,000 years. Caves form over thousands to millions of years as slightly acidic water dissolves limestone and other soluble rocks. The longest known cave system in the world is Mammoth Cave in Kentucky, with over 400 miles of surveyed passages. Explorers continue to discover new sections, connecting previously separate cave systems, and the true extent of this underground labyrinth remains unknown. Some estimates suggest there may be 600 miles or more of passages yet to be discovered. The largest cave chamber in the world is the Sarawak Chamber in Malaysia, large enough to hold 40 Boeing 747 aircraft. The tallest stalagmite ever found is in Zhijian Cave in China, standing over 230 feet tall, built up drip by drip over hundreds of thousands of years. Each drop of water leaves behind a tiny deposit of minerals, and over time, these deposits grow into the fantastic formations that decorate caves around the world. The continents beneath us are not fixed in place, but drift slowly across the face of the Earth, carried by the movement of the tectonic plates upon which they ride. This movement, though imperceptible in a human lifetime, typically only a few centimeters per year, has dramatically reshaped our world over geological time. Mountains have risen and eroded away. Oceans have opened and closed. What is now desert was once tropical rainforest, and what is now polar ice was once warm sea. The theory of plate tectonics, developed in the mid-20th century, revolutionized our understanding of how Earth works. It explains why earthquakes and volcanoes occur where they do, why mountains form in certain places, and why the coastlines of Africa and South America fit together like puzzle pieces. This elegant theory unified many observations that had puzzled geologists for centuries. Approximately 300 million years ago, all the continents were joined together in a single supercontinent called Pangaea, surrounded by a vast global ocean called Panthalassa. If you could have stood on Pangaea's shore, you might have walked from what is now New York to Morocco without crossing any sea. Dinosaurs could have wandered from Antarctica to Alaska without getting their feet wet. This supercontinent began to break apart about 200 million years ago, and the fragments have been drifting ever since. Pangaea was not the first supercontinent, nor will our current arrangement of continents be the last. Before Pangaea, there were other supercontinents. Rodinia, about 1 billion years ago, and perhaps Nuna and Kenorland before that. The continents seem to cycle through phases of assembly and dispersal over periods of about 300 to 500 million years, a process sometimes called the supercontinent cycle. The Atlantic Ocean grows wider by about 1 inch per year as the Americas drift away from Europe and Africa. This is about the same rate at which your fingernails grow. Meanwhile, the Pacific Ocean is slowly shrinking as its oceanic plates subduct beneath the continents that surround it. In about 250 million years, the continents may come together again to form a new supercontinent, which some geologists have named Pangaea Ultima or Amasia. Earth's tectonic plates are pieces of the lithosphere, the rigid outer layer of the planet that includes the crust and the uppermost part of the mantle. The lithosphere is broken into about 15 major plates and several dozen smaller ones. These plates float on the asthenosphere, a partially molten layer of the upper mantle that flows slowly over geological time, carrying the plates along with it. Earthquakes occur when stress builds up along the boundaries between tectonic plates and is suddenly released. The rocks along a fault line may be locked in place for decades or centuries, slowly deforming under the pressure of the moving plates until they suddenly slip, releasing energy as seismic waves. About 500,000 earthquakes occur around the world each year, though only about 100,000 of these can be felt and only about 100 cause damage. The vast majority are so subtle that only sensitive instruments can detect them. The largest earthquake ever recorded was the Great Chilean Earthquake of 1960, which registered a magnitude of 9.5. This earthquake was so powerful that it caused the entire planet to vibrate for days afterward, ringing like a bell. It generated a tsunami that crossed the Pacific Ocean, causing death and destruction as far away as Japan and the Philippines, more than 10,000 miles from the epicenter. The Ring of Fire, a horseshoe-shaped zone around the Pacific Ocean, is home to about 75% of the world's active volcanoes and about 90% of the world's earthquakes. This intense geological activity occurs because the Pacific Plate is subducting beneath the surrounding continental plates. As the oceanic crust dives into the mantle, it releases water that lowers the melting point of the overlying rock, generating the magma that feeds the volcanoes of the Ring of Fire. Iceland sits directly on the Mid-Atlantic Ridge, one of the few places where this underwater mountain range rises above sea level. The island is literally being pulled apart as the North American and Eurasian plates drift away from each other, creating a rift valley that runs through the center of the country. You can visit places in Iceland where you can see the boundary between two tectonic plates, even walking through a canyon with North America on one side and Europe on the other. The movement of tectonic plates also drives the process of mountain building, volcanic activity, and the formation of deep ocean trenches. Without plate tectonics, Earth would likely be a very different world, perhaps without the dynamic geology that has helped make our planet so hospitable to life. Some scientists believe that plate tectonics is essential for keeping Earth's climate stable over geological time by regulating the carbon cycle. Earth is the only planet we know of that harbors life, a precious oasis of biology in the vast emptiness of space. From the deepest ocean trenches to the highest mountain peaks, from boiling hot springs to frozen Antarctic ice, life has found a way to thrive in almost every environment our planet offers. This diversity of life, developed over billions of years, is one of Earth's most remarkable features. life emerged on our planet remarkably early in its history. The oldest known fossils of simple single-celled organisms, called stromatolites, date back approximately 3.5 billion years. These structures, formed by mats of bacteria, can still be seen forming today in a few special places, like Shark Bay in Australia. They offer us a glimpse of what the living Earth might have looked like billions of years ago. The exact origin of life remains one of science's great mysteries. How did simple chemicals combine to form the first self-replicating molecules? How did these molecules become enclosed in cell membranes? How did the first cells develop the complex machinery of life? Scientists have proposed many theories, from deep-sea hydrothermal vents to shallow pools struck by lightning, but the precise pathway remains unknown. What we do know is that once life emerged, it proved remarkably persistent and adaptable. For most of Earth's history, life remained microscopic. For about 3 billion years, the only life on Earth was single-celled organisms, bacteria and archaea, invisible to the naked eye. These simple organisms transformed our planet, producing oxygen through photosynthesis, changing the composition of the atmosphere, and setting the stage for the explosion of complex life that was to come. Complex multicellular organisms did not appear until about 600 million years ago, during a period called the Ediacaran. The fossils from this time show strange, soft-bodied creatures unlike anything alive today, forms that seem almost alien in their unfamiliarity. These were the first large, complex organisms on Earth, and their appearance marked a turning point in the history of life. Then, about 540 million years ago, life underwent a dramatic burst of diversification called the Cambrian explosion. In a geologically brief period of perhaps 20 million years, most of the major animal groups first appeared in the fossil record. Suddenly, the seas were filled with creatures that had hard shells, complex eyes, and active predation. This explosion of diversity set the stage for all the animal life that has followed. Earth is home to an estimated 8.7 million species of plants and animals, though only about 1.5 million have been formally described and named. Scientists believe that millions of species remain unknown to science, particularly in remote rainforests, the deep ocean, and in the soil beneath our feet. Every year, scientists discover thousands of new species, from tiny insects to previously unknown mammals. The Amazon rainforest alone contains about 10% of all species on Earth, making it the most biodiverse place on the planet. A single hectare of Amazonian forest may contain over 750 types of trees, more than the number of tree species in all of North America. The forest is home to more than 1,500 species of higher plants, over 2,000 species of fish, more than 400 species of amphibians, and countless insects and other invertebrates. Trees are among the oldest living organisms on Earth. The oldest known individual tree is a bristlecone pine named Methuselah, growing high in the White Mountains of California, which is over 4,800 years old. This ancient tree was already old when the pyramids of Egypt were being built, when the first alphabets were being developed, when bronze was the cutting edge of technology. It has lived through the rise and fall of countless civilizations. Some organisms achieve even greater age through clonal reproduction. A stand of quaking aspen trees in Utah called Pando is considered to be one of the oldest living organisms on Earth. This colony of genetically identical trees, all connected by a single root system, is estimated to be about 80,000 years old, predating the last ice age and the migration of modern humans out of Africa. The largest living organism on Earth is a honey fungus in Oregon's Blue Mountains. This single fungus, belonging to the species Armillaria osti, covers approximately 2,385 acres, an area about the size of 1,600 football fields. The fungus is estimated to be between 2,400 and 8,650 years old and weighs approximately 6,600 tons. Bacteria and other microorganisms make up the vast majority of life on Earth by both number and total mass. There are more bacterial cells in a single human body than there are human cells, living in your gut, on your skin, and throughout your tissues. These microbes are not invaders but partners, helping you digest food, fight off pathogens, and maintain your health in countless ways. The total mass of bacteria on Earth is estimated to exceed that of all plants and animals combined. Life has proven remarkably resilient, surviving through at least 5 mass extinction events that each eliminated a significant percentage of all species. The most severe, the Permian-Triassic extinction, about 252 million years ago, wiped out about 90% of all species on Earth. Yet after each catastrophe, life rebounded and diversified, eventually producing even more species than before. This pattern suggests that life, once established, is difficult to completely eradicate. Earth is surrounded by an invisible shield called the magnetosphere, generated by the churning of molten iron in our planet's outer core. This magnetic field extends tens of thousands of miles into space, forming a protective bubble that deflects charged particles from the sun. Without this shield, the solar wind would gradually strip away our atmosphere and bombard the surface with harmful radiation. The solar wind is a continuous stream of charged particles flowing outward from the sun at speeds of about 1 million miles per hour. When these particles encounter Earth's magnetic field, they are deflected around the planet like water flowing around a stone in a stream. Some particles become trapped in regions called the Van Allen radiation belts, circling the Earth along the magnetic field lines. The magnetic field is generated through a process called the geodynamo. As the liquid iron in the outer core flows and swirls, driven by convection currents and the rotation of the Earth, it creates electrical currents. These currents, in turn, generate magnetic fields, which then influence the flow of the liquid iron, creating a self-sustaining feedback loop that has maintained Earth's magnetic field for billions of years. The magnetic poles do not align exactly with the geographic poles. The magnetic North Pole is currently located in the Canadian Arctic, but it moves continuously, drifting at about 25 miles per year and currently heading towards Siberia. This wandering of the poles requires regular updates to navigational charts and compasses. Throughout Earth's history, the magnetic poles have completely reversed many times, with north becoming south and south becoming north. Evidence of these reversals is recorded in rocks on the ocean floor, where iron minerals align with the magnetic field as molten rock solidifies. The resulting striped pattern of magnetized rock provided some of the first evidence for seafloor spreading and plate tectonics. The last magnetic reversal occurred about 780,000 years ago. These reversals happen irregularly, sometimes with millions of years between them and sometimes with only tens of thousands of years. Scientists don't fully understand what triggers a reversal, but it appears to involve changes in the flow patterns of the outer core. During a reversal, the magnetic field weakens significantly, but does not disappear entirely. The field may become more complex, with multiple north and south poles appearing simultaneously. This weakened state may last for several thousand years before the field stabilizes in its reversed orientation. There is some evidence that we may be in the early stages of a reversal now, as the field has been weakening over the past few centuries. When charged particles from the sun do manage to enter Earth's atmosphere near the magnetic poles, they collide with gas molecules and create one of nature's most spectacular displays, the aurora. In the northern hemisphere, this phenomenon is called the aurora borealis or northern lights. In the southern hemisphere, it is the aurora australis or southern lights. The charged particles, mainly electrons and protons, are guided by Earth's magnetic field lines toward the polar regions. When they collide with oxygen and nitrogen molecules in the upper atmosphere, they transfer energy to these molecules, causing them to emit light as they return to their normal state. This is similar to how a neon light works, but on a planetary scale. The colors of the aurora depend on which atmospheric gases are struck by the charged particles and at what altitude. Green, the most common color, is produced by oxygen molecules at altitudes of about 60 to 150 miles. This green is a very specific wavelength of light, emitted when excited oxygen atoms release their excess energy. Red auroras come from oxygen at higher altitudes, above 150 miles, where the lower density of the atmosphere allows the oxygen atoms more time to emit this less probable red wavelength. Blue and purple hues result from nitrogen molecules being ionized, meaning electrons are stripped away from the atoms. Nitrogen can produce blue light when it regains electrons and pink or red when it returns to ground state after being excited. The combination of these colors creates the shimmering, dancing curtains of light that make auroras so mesmerizing. Auroras have been observed throughout human history and have inspired countless myths and legends. The Norse people believed the lights were reflections from the armor of the Valkyries, the warrior maidens who escorted fallen heroes to Valhalla. Some indigenous peoples of North America saw them as the spirits of their ancestors dancing in the sky or the fires of great hunters cooking their catch. In Finnish folklore, the aurora was caused by a magical fox sweeping its tail across the snow, sending sparks into the sky. The sun's activity follows an approximately 11-year cycle, with periods of intense activity called solar maximum producing more frequent and spectacular auroral displays. During solar maximum, the sun releases more energy and charged particles, increasing the chances of geomagnetic storms that drive auroras to lower latitudes than usual. During particularly strong solar storms, auroras have been seen as far south as Mexico and the Caribbean. Earth rotates on its axis once every 23 hours, 56 minutes, and 4 seconds relative to the distant stars. This period, called a sidereal day, is slightly shorter than the familiar 24-hour solar day because Earth must rotate a bit extra to compensate for its movement along its orbit around the sun. This rotation gives us the cycle of day and night that has governed the rhythms of life since the earliest times. The Earth spins at different speeds depending on where you are. At the equator, the surface is moving at about 1,037 miles per hour, faster than the speed of sound. At the poles, the rotation speed is essentially zero. This is why rockets are often launched from locations close to the equator to take advantage of the extra speed the Earth's rotation provides. The Earth's rotation is gradually slowing due to the gravitational pull of the moon, which creates tidal friction in the oceans. As the moon's gravity pulls on the oceans, it creates tidal bulges that are dragged slightly ahead of the moon by Earth's rotation. The moon's gravity then pulls back on these bulges, slowing the Earth's spin. Each day is about 1.4 milliseconds longer than it was a century ago. Hundreds of millions of years ago, days were significantly shorter. During the age of dinosaurs, about 70 million years ago, days lasted only about 23 hours. Going back further, about 620 million years ago, during the Ediacaran period, a day was only about 22 hours long. In the very early history of Earth, soon after the moon formed, days may have been as short as 6 hours. As Earth's rotation slows, the moon drifts farther away, currently receding at a rate of about 1.5 inches per year. This happens because the energy lost from Earth's rotation is transferred to the moon's orbit, causing it to spiral slowly outward. Billions of years from now, the Earth and moon will become tidally locked, always showing the same face to each other, and a day on Earth will be about 47 of our current days long. The length of a day varies slightly throughout the year due to the effects of winds, ocean currents, and the melting and freezing of ice caps. Even the sloshing of water in the oceans during El Niño events can affect the length of the day by a fraction of a millisecond. To keep our clocks synchronized with the slightly variable rotation of the Earth, leap seconds are occasionally added to coordinated universal time. Earth orbits the Sun at an average distance of about 93 million miles, a measurement known as 1 astronomical unit. Our planet travels along this orbit at approximately 67,000 miles per hour, much faster than a speeding bullet, completing 1 full revolution every 365.25 days. We add an extra day to the calendar every 4 years, during leap years, to account for this quarter day. The orbit of Earth around the Sun is not a perfect circle, but a slightly elongated ellipse. The difference between the closest and farthest points is about 3%, a variation large enough to affect how much solar energy we receive, but not the primary cause of our seasons. The tilt of Earth's axis, approximately 23.4 degrees from vertical, gives us our seasons. This tilt means that as Earth orbits the Sun, different parts of the planet receive more direct sunlight at different times of year. When the northern hemisphere tilts toward the Sun, it experiences summer while the southern hemisphere has winter. 6 months later, the situation reverses. The point where Earth is closest to the Sun is called perihelion, occurring around January 3rd each year, when we are about 91 million miles from the Sun. Aphelion, our farthest point, occurs around July 4th, when we are about 94.5 million miles away. Perhaps counterintuitively, the northern hemisphere has summer when Earth is actually farthest from the sun, because the tilt of the axis matters more than the distance for determining seasons. Time zones were established in the 19th century to standardize timekeeping, as railroads and telegraph communications made it necessary to coordinate activities across great distances. Before this, each town set its clocks according to the local position of the sun, leading to a confusing patchwork of local times that made scheduling train arrivals nearly impossible. The adoption of standard time zones, based on the prime meridian at Greenwich, England, brought order to this chaos. The weather we experience each day is the result of complex interactions between the atmosphere, oceans, land, and energy from the sun. These systems work together in intricate ways that meteorologists are still working to fully understand, using supercomputers to model the behavior of trillions of air molecules swirling in ever-changing patterns across the globe. The sun provides virtually all the energy that drives Earth's weather systems. Each day, the sun delivers about 170 petawatts of power to the Earth, about 10,000 times humanity's total energy consumption. This energy heats the Earth unevenly, with the equator receiving more warmth than the poles, and land heating and cooling more quickly than water. These temperature differences create the pressure gradients that drive winds and weather patterns around the globe. Clouds form when water vapor in the atmosphere condenses around tiny particles called condensation nuclei. These particles can be dust, pollen, sea salt, volcanic ash, or even bacteria. Without these nuclei, water vapor would have difficulty condensing, and we would have far fewer clouds. A single cumulus cloud, though it appears light and fluffy floating in the sky, can contain hundreds of tons of water suspended as tiny droplets, each droplet so small it floats on the faintest upward breeze. Clouds come in many varieties, classified by their height and shape. Cirrus clouds, the wispy, feathery clouds high in the sky, are made of ice crystals and often indicate fair weather. Cumulus clouds, the puffy white clouds that look like cotton balls, form from rising columns of warm air. Cumulonimbus clouds, the towering thunderheads, can reach heights of over 50,000 feet and produce heavy rain, lightning, hail, and even tornadoes. Lightning occurs when electrical charges separate within a thundercloud, with positive charges accumulating at the top and negative charges at the bottom. As the voltage difference grows, step leaders of negative charge begin to reach down from the cloud toward the ground. When one of these connects with a positive streamer rising from the ground, a conductive channel is formed, and the main stroke of lightning flashes upward at about 220 million miles per hour. The air in a lightning channel is heated to over 50,000 degrees Fahrenheit, 5 times hotter than the surface of the sun. This superheated air expands explosively, creating the shock wave we hear as thunder. Because light travels much faster than sound, we see the lightning before we hear the thunder. By counting the seconds between the flash and the rumble and dividing by 5, you can estimate approximately how many miles away the lightning struck. At any given moment, there are about 1,800 thunderstorms occurring somewhere on Earth, producing about 100 lightning strikes per second, or more than 8 million lightning strikes per day. Lightning strikes the Earth about 40 to 50 times per second, each bolt carrying about 1 billion joules of energy, enough to power a 100-watt light bulb for 3 months. Thunder is the sound produced when lightning rapidly heats the air, causing it to expand explosively. The rumbling quality of thunder comes from the fact that lightning bolts are typically several miles long, so the sound from different parts of the bolt reaches your ears at different times. This creates the characteristic rolling sound that can last for several seconds. Hurricanes, typhoons, and cyclones are all names for the same phenomenon: large rotating storm systems that form over warm tropical oceans. These storms are called hurricanes in the Atlantic and Eastern Pacific, typhoons in the Western Pacific, and cyclones in the Indian Ocean and South Pacific. They draw their energy from the evaporation of warm seawater and can grow to enormous size, sometimes spanning several hundred miles across. A hurricane is like a giant heat engine, powered by the warm tropical ocean. As warm, moist air rises from the ocean surface, it releases heat as the water vapor condenses into clouds. This released heat warms the air further, causing it to rise faster and drawing in more moist air from below. This positive feedback loop intensifies the storm until it becomes a massive spiral of wind and rain. The eye of a hurricane, the calm center of the storm, is typically 20 to 40 miles in diameter. Within the eye, the air is relatively calm and the sky may even be clear. But surrounding the eye is the eye wall, the most intense part of the storm, where the strongest winds and heaviest rainfall occur. Wind speeds in the eye wall can exceed 150 miles per hour in the most powerful hurricanes. The average global surface temperature is approximately 59 degrees Fahrenheit. However, Earth has experienced dramatically different climates throughout its history. During the Cryogenian period, about 700 million years ago, Earth may have been entirely covered in ice, a state sometimes called snowball Earth. At other times, during the Mesozoic era when dinosaurs roamed, the Earth was so warm that there were no ice caps at all, and palm trees grew near the poles. Rain varies enormously around the globe. Mawsynram in the Indian state of Meghalaya holds the record for the wettest place on Earth, receiving an average of about 467 inches of rain per year, mostly during the monsoon season. During the wettest months, rain falls almost continuously, and the residents have developed living root bridges made from the roots of rubber fig trees, which grow stronger over time and can span over 100 feet. In contrast, the Atacama Desert in Chile is the driest place on Earth, with some weather stations never having recorded a single drop of rain. Parts of the Atacama have been essentially rainless for millions of years. The soil is so dry and sterile that NASA has used it to test equipment designed to search for life on Mars. Yet even here, life finds a way, with specialized microbes surviving in rocks and fog-catching plants drawing moisture from the Pacific. Our Earth is a small rocky planet orbiting an ordinary yellow dwarf star in the outer reaches of an unremarkable spiral galaxy. Yet from this seemingly modest cosmic address, we have emerged to contemplate the universe and our place within it. From our tiny world, we have sent spacecraft to every planet in our solar system and beyond. We have detected the ripples in spacetime from colliding black holes billions of light years away, and we have begun to understand the origin and evolution of the cosmos itself. The Sun, our parent star, is about 864,000 miles in diameter, large enough to contain about 1.3 million Earths. If the Sun were hollow, you could fit the Earth inside it more than 1 million times over. The Sun contains about 99.8% of all the mass in our solar system. Everything else, all the planets, moons, asteroids, and comets combined, makes up only a tiny fraction of the solar system's mass. Yet compared to the largest known stars, our Sun is quite modest. The star Uy-Scuti, one of the largest known, has a radius about 1,700 times that of the Sun. If Uy-Scuti were placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter. Stars like Uy-Scuti are extremely rare and short-lived, burning through their nuclear fuel in just a few million years. Light from the Sun takes about 8 minutes and 20 seconds to reach Earth, traveling at about 186,000 miles per second. This means that if the Sun were to suddenly vanish, we would continue to see it and feel its warmth for more than 8 minutes before learning of the catastrophe. The light reaching your eyes from the Sun right now began its journey before you started listening to these facts. Our solar system is located in the Orion arm of the Milky Way galaxy, a minor spiral arm between the larger Sagittarius and Perseus arms. We are about 26,000 light-years from the galactic center, which hosts a supermassive black hole called Sagittarius A*, with a mass of about 4 million suns. The Milky Way contains an estimated 100 to 400 billion stars, and our solar system orbits the galactic center once every 230 million years, a period sometimes called a galactic year. In the entire history of Earth, our planet has completed only about 20 orbits of the galaxy. Dinosaurs lived only about 1 galactic orbit ago. The last time Earth was at this same position in its galactic orbit, the most advanced life on Earth was probably simple multicellular organisms in the oceans. The nearest star to our Sun is Proxima Centauri, about 4.24 light-years away, part of the Alpha Centauri triple star system. This means that the light we see from Proxima Centauri tonight actually left that star about 4.25 years ago. If you were to travel at the speed of the fastest spacecraft ever launched, the Parker Solar Probe at its maximum speed, it would take about 6,000 years to reach this nearest stellar neighbor. Proxima Centauri is known to have at least one planet, Proxima Centauri b, which orbits within the star's habitable zone. This planet is slightly larger than Earth and receives about the same amount of energy from its star as Earth receives from the Sun. Whether this planet is truly habitable remains unknown, as Proxima Centauri is a red dwarf star prone to powerful flares that might strip away any atmosphere. Earth is located within what astronomers call the habitable zone of our solar system, the region around a star where liquid water can exist on a planet's surface. This zone is sometimes called the Goldilocks zone because conditions must be not too hot and not too cold, but just right for life as we know it. If Earth were much closer to the Sun, our oceans might boil away, as likely happened on Venus. Much farther, and they would freeze solid, as on Mars. The Milky Way is part of a collection of galaxies called the Local Group, which includes about 80 galaxies spread across roughly 10 million light-years of space. Most of these are small dwarf galaxies, invisible to the naked eye. Our largest neighbor is the Andromeda Galaxy, visible to the naked eye on clear, dark nights as a faint smudge of light in the constellation Andromeda. Andromeda is about 2.5 million light-years away, meaning the light you see from it tonight began its journey when our ancestors were first learning to use stone tools. The Milky Way and Andromeda are approaching each other at about 70 miles per second and will collide in about 4 to 5 billion years. This collision will not be the violent crash you might imagine. The stars in each galaxy are so spread out that most will pass by each other with plenty of room to spare. But the gravitational interactions will dramatically reshape both galaxies, likely merging them into a single giant elliptical galaxy, sometimes called Milkomeda. The universe itself is approximately 13.8 billion years old, meaning Earth has existed for about a third of cosmic history. The Big Bang, which marks the beginning of the universe as we know it, was not an explosion in space, but an expansion of space itself. In the first fractions of a second, the universe expanded faster than the speed of light, and the seeds of all the structures we see today were planted. The elements that make up our planet and our bodies were forged in the hearts of ancient stars that exploded long before our solar system formed. Hydrogen and helium were made in the Big Bang itself. Carbon, oxygen, nitrogen, and other light elements were synthesized in the cores of stars through nuclear fusion. Elements heavier than iron, like gold, silver, and uranium, were created in the violent deaths of massive stars or in the collisions of neutron stars. We are, quite literally, made of star stuff. As we near the end of our journey, let us contemplate some of the natural wonders that make our planet so remarkable. From towering waterfalls to vast deserts, from lush rainforests to frozen tundra, Earth displays an astonishing variety of landscapes and ecosystems, each one shaped by billions of years of geological and biological evolution. The Great Barrier Reef off the coast of Australia is the largest structure made by living organisms, stretching for over 1,400 miles along the Queensland coast. This immense coral reef system is home to an incredible diversity of marine life, including over 1,500 species of fish, over 400 types of coral, and countless other organisms. The reef is so large that it can be seen from space, a ribbon of turquoise and blue along the Australian coast. Victoria Falls, on the border between Zambia and Zimbabwe, creates the largest curtain of falling water in the world when the Zambezi River is in full flood. The falls are about 5,500 feet wide and over 350 feet tall, sending more than 500 million liters of water per minute plunging into the gorge below. The spray from the falls can rise over 1,000 feet into the air and can be seen from more than 30 miles away. The local people call it Mosioatunya, meaning the smoke that thunders, describing the mist that rises from the gorge below. The Sahara Desert is the largest hot desert on Earth, covering about 3.5 million square miles of North Africa, an area roughly the size of the United States. Yet this vast expanse of sand and rock was not always so dry. Rock paintings in the Sahara depict hippos, crocodiles, giraffes, and other animals that require abundant water, evidence that the Sahara was green and wet just a few thousand years ago. Climate cycles driven by changes in Earth's orbit cause the Sahara to shift between wet and dry phases every 20,000 years or so. Antarctica, the coldest and driest continent, holds about 70% of all the freshwater on Earth locked in its ice sheets. These ice sheets are up to 3 miles thick in places, containing enough frozen water to raise global sea levels by about 200 feet if it all melted. Antarctica is also the windiest continent, with katabatic winds, cold air flowing down from the high interior, sometimes exceeding 200 miles per hour. Despite its harsh conditions, Antarctica supports a surprising variety of life. Emperor penguins breed on the sea ice in the depths of winter, enduring temperatures below -40 degrees and winds over 100 miles per hour. Seals, whales, and countless seabirds depend on the rich waters surrounding the continent. And in the ice itself, scientists have found microorganisms surviving in conditions that would seem impossible for life. Earth is constantly being bombarded by material from space. About 100 tons of cosmic dust and small meteorites fall to Earth every day, though most of this material is too small to notice, drifting down invisibly through the atmosphere. Occasionally, larger objects arrive, creating the fireballs we sometimes see streaking across the night sky. Rarely, much larger objects impact the Earth, leaving craters and sometimes triggering mass extinctions. The biosphere, atmosphere, hydrosphere, and geosphere work together in intricate cycles that have sustained life for billions of years. Carbon cycles between air, water, rock, and living things, moving from the atmosphere into plants through photosynthesis, from plants into animals through feeding, and back to the atmosphere through respiration and decomposition. Water evaporates from the oceans, falls as rain, flows through rivers, and returns to the sea, endlessly cycling through the environment. Nutrients are recycled through ecosystems, supporting generation after generation of life. These cycles are delicately balanced, maintaining conditions suitable for life over billions of years. The oxygen you breathe was produced by countless generations of photosynthetic organisms. The soil beneath your feet was built up over thousands of years by the work of plants, animals, fungi, and microorganisms. Every breath you take, every drink of water, every bite of food, connects you to these ancient cycles that sustain all life on Earth. Let your thoughts now flow like water, drifting to the rivers and streams that crisscross our planet like the veins of a living body. Rivers have shaped civilizations, carved landscapes, and sustained life since the earliest days of Earth's history. They carry water from the mountains to the sea, completing the endless cycle that keeps our planet alive. The Amazon River is the largest river on Earth by volume, discharging approximately 209,000 cubic meters of water into the Atlantic Ocean every second. This single river accounts for about 20% of all the freshwater that flows into the world's oceans. During the rainy season, the Amazon can be 30 miles wide in some places, a vast inland sea winding through the world's largest rainforest. The Amazon basin covers about 2.7 million square miles, an area nearly the size of the contiguous United States. More than 1,000 tributaries feed into the Amazon, 17 of which are over 1,000 miles long. The river is home to more species of fish than the entire Atlantic Ocean, including the feared piranha, the massive arapaima that can grow over 10 feet long, and the pink river dolphin, one of only a few species of freshwater dolphins in the world. The Nile River, stretching approximately 4,130 miles from its headwaters in Burundi to its delta on the Mediterranean Sea, is often considered the longest river in the world, though some measurements place the Amazon slightly longer. The Nile flows northward through 11 countries, providing water to millions of people in one of the driest regions on Earth. Ancient Egyptian civilization arose along its banks, dependent on the annual floods that deposited rich, fertile silt across the floodplain. The Ganges River in India is considered sacred by over 1 billion Hindus, who believe that bathing in its waters can wash away sins, and that dying beside the river ensures release from the cycle of rebirth. Despite being one of the most polluted rivers in the world, pilgrims travel from across India to immerse themselves in its waters. The river supports about 400 million people, one of the highest population densities of any river basin on Earth. Rivers have carved some of the most spectacular landscapes on our planet. The Colorado River spent approximately 6 million years carving the Grand Canyon, cutting through layer after layer of ancient rock to expose nearly 2 billion years of geological history. The river continues to deepen the canyon today, though at a much slower rate than in the past, removing about 1 foot of rock every 1,000 years. Waterfalls form where rivers encounter sudden changes in the hardness of underlying rock or where geological faults create cliffs. Angel Falls in Venezuela is the world's highest uninterrupted waterfall, plunging 3,212 feet from the top of Ollantaytambo, a flat-topped mountain in the Venezuelan highlands. The falls are so high that much of the water evaporates or is blown away as mist before reaching the bottom. Niagara Falls, straddling the border between the United States and Canada, is not particularly tall at only about 167 feet, but it is one of the most powerful waterfalls in the world. About 6 million cubic feet of water flow over the falls every minute during peak daytime hours, generating tremendous hydroelectric power. The falls are slowly eroding upstream at a rate of about 1 foot per year, having retreated about 7 miles since their formation at the end of the last ice age. Lakes are another vital component of Earth's freshwater system. The Great Lakes of North America contain about 21% of the world's surface freshwater, enough water to cover the entire contiguous United States to a depth of about 10 feet. Lake Superior alone is the largest freshwater lake by surface area, covering 31,700 square miles, an area larger than South Carolina. Lake Baikal in Siberia is the deepest lake on Earth, reaching a maximum depth of 5,387 feet. This ancient lake, formed about 25 to 30 million years ago in a rift valley, contains about 22% of the world's surface freshwater, more than all the Great Lakes combined. Lake Baikal is home to approximately 1,700 species of plants and animals, 2/3 of which are found nowhere else on Earth, including the Nerpa, the world's only exclusively freshwater seal. Underground water, stored in aquifers, represents a vast hidden reservoir of freshwater. The Ogallala Aquifer beneath the Great Plains of the United States contains about 3 billion acre-feet of water, accumulated over millions of years. This groundwater supports agriculture across 8 states, but it is being depleted faster than it can be recharged by rainfall. In some areas, the water table has dropped by more than 150 feet since pumping began. Groundwater can take thousands or even millions of years to accumulate. Some of the water being pumped from deep aquifers today fell as rain during the last ice age, more than 10,000 years ago. This ancient water, isolated from the surface for millennia, can have a very different chemical composition than modern precipitation, sometimes containing minerals or trace elements that give it distinctive properties. Breathe deeply now and imagine the quiet stillness of an ancient forest. Trees stand like silent sentinels, their roots reaching deep into the earth, their branches stretching toward the sky. Forests cover about 31% of Earth's land surface, providing habitat for countless species, producing the oxygen we breathe, and playing a crucial role in regulating our planet's climate. Forests produce approximately 28% of the oxygen in Earth's atmosphere through photosynthesis, the remarkable process by which plants convert carbon dioxide and water into sugar and oxygen using energy from sunlight. However, forests also consume much of the oxygen they produce through respiration, so the net contribution to atmospheric oxygen is relatively small. The majority of our oxygen actually comes from marine phytoplankton, tiny photosynthetic organisms drifting in the sunlit surface waters of the oceans. The Amazon rainforest alone contains an estimated 390 billion trees, representing about 16,000 different species. A single hectare of Amazon forest may contain more than 75,000 different species of trees, more species than are found in all of North America. The forest is so dense that rain falling on the canopy can take 10 minutes to reach the forest floor, dripping from leaf to leaf through multiple layers of vegetation. Trees communicate with each other through an underground network of fungal filaments called mycorrhizae, sometimes called the wood wide web. Through this network, trees can share nutrients, water, and chemical signals. Mother trees can recognize their own offspring and preferentially send them nutrients through the fungal network. When a tree is dying, it may dump its resources into the network, providing a final gift to its neighbors. The oldest individual trees on Earth are bristlecone pines growing in the White Mountains of California. The oldest known specimen, named Methuselah, is more than 4,850 years old, meaning it was already ancient when the Egyptian pyramids were being built. These trees grow in harsh conditions at high altitude, where cold temperatures, dry air, and poor soil actually help preserve them by limiting the growth of fungi and bacteria that might cause decay. An even older organism exists in the form of a clonal colony. Pando, a stand of quaking aspen trees in Utah, is considered one of the oldest living organisms on Earth. What appears to be a forest of individual trees is actually a single organism, with all the trees connected by a massive underground root system. Pando is estimated to be about 80,000 years old and weighs approximately 13 million pounds, making it also one of the heaviest known organisms. The tallest trees on Earth are coast redwoods growing in California. The tallest known individual, named Hyperion, stands 383 feet tall, taller than the Statue of Liberty, including its pedestal. These ancient trees can live for more than 2,000 years and have bark up to 12 inches thick that protects them from fire. Coast redwoods once covered a much larger area of the Pacific coast, but are now limited to a narrow strip of foggy coastline where they depend on summer fog for much of their water. The largest trees by volume are giant sequoias, also found in California. The largest known individual, named General Sherman, has a trunk volume of about 52,500 cubic feet and weighs approximately 2.7 million pounds. General Sherman is not the tallest tree, nor the widest, nor the oldest, but the combination of its height, width, and age give it the greatest total volume of any known tree. Forests play a crucial role in the carbon cycle, absorbing carbon dioxide from the atmosphere and storing it in their wood, leaves, and soil. The world's forests store approximately 400 billion tons of carbon, roughly equivalent to 50 years of current global carbon dioxide emissions. When forests are destroyed, this stored carbon is released back into the atmosphere, contributing to climate change. The boreal forest, also called the taiga, is the world's largest land biome, stretching across northern Russia, Scandinavia, Canada, and Alaska. This vast forest of coniferous trees covers about 17% of Earth's land surface and stores more carbon in its soils than all the tropical rainforests combined. The boreal forest experiences extreme seasonal variation, with temperatures ranging from -65 degrees Fahrenheit in winter to over 85 degrees in summer. Mangrove forests grow along tropical coastlines, their tangled roots extending into salt water. These remarkable trees have adapted to survive in conditions that would kill most plants, filtering salt from seawater and sending up snorkel-like roots to breathe. Mangroves protect coastlines from erosion and storm damage, serve as nurseries for many species of fish and shellfish, and store carbon at rates up to 5 times higher than terrestrial forests. As you drift deeper into relaxation, let your mind wander to the quiet expanses of the world's deserts, places of stark beauty and surprising life. Deserts cover about 1/3 of Earth's land surface, defined not by heat, but by lack of precipitation. Any region that receives less than 10 inches of rain per year is classified as a desert, which means that even the frozen continent of Antarctica is technically a desert. The Sahara Desert is the world's largest hot desert, covering about 3.5 million square miles of North Africa. This vast expanse of sand and rock is roughly the size of the United States. Temperatures in the Sahara can exceed 130 degrees Fahrenheit during the day, yet drop to near freezing at night. This dramatic temperature swing occurs because dry air holds heat poorly, allowing rapid cooling after sunset. The Sahara was not always a desert. Rock paintings found throughout the region depict hippos, crocodiles, elephants, and people swimming and boating, evidence that the Sahara was green and wet as recently as 5,000 years ago. This greening and drying cycle is driven by changes in Earth's orbit that affect the strength of the African monsoon. Every 20,000 years or so, the Sahara transitions between desert and savanna. Beneath the Sahara lies one of the world's largest aquifers, the Nubian Sandstone Aquifer System, containing approximately 150,000 cubic kilometers of fossil water. This water accumulated over millions of years when the climate was wetter and has been largely cut off from recharge ever since. Several nations are now tapping this ancient water for agriculture and drinking water, though it is a non-renewable resource on human timescales. The Atacama Desert in Chile is the driest place on Earth. Some weather stations in the Atacama have never recorded a single drop of rain. The soil is so dry and sterile that it has been used by NASA to test equipment designed to search for life on Mars. Yet even here, life finds a way. Specialized microorganisms live inside translucent rocks, using the filtered sunlight for photosynthesis. Fog-catching beetles harvest moisture from the Pacific fog that occasionally rolls inland. Death Valley, California, holds the record for the highest reliably recorded air temperature on Earth, 134 degrees Fahrenheit, measured on July 10, 1913. The valley is also one of the lowest points on Earth, with its floor sitting 282 feet below sea level. This combination of low elevation and surrounding mountains creates a natural oven that traps and intensifies heat. Despite their harsh conditions, deserts support a remarkable diversity of life. Desert plants have evolved numerous strategies for surviving with little water, including deep root systems that can reach groundwater far below the surface, waxy coatings that reduce water loss, and the ability to remain dormant for years until rain arrives. The saguaro cactus of the Sonoran Desert can store up to 200 gallons of water in its ribbed trunk, enough to survive years of drought. Desert animals have also evolved remarkable adaptations. The kangaroo rat of the American Southwest can survive its entire life without drinking water, obtaining all the moisture it needs from the seeds it eats. It further conserves water by having extremely efficient kidneys that produce highly concentrated urine, and by being active only at night when temperatures are cooler. The Arabian desert sand cat can survive for months without drinking water, while the fennec fox's enormous ears help dissipate excess body heat. The thorny devil lizard of Australia collects dew on its skin, which is then channeled by tiny grooves to the corners of its mouth. Each desert creature represents millions of years of evolution, honing the art of survival in Earth's most challenging environments. Polar deserts represent the opposite extreme of temperature, but share the characteristic of extreme dryness. The Antarctic interior receives less than 2 inches of precipitation per year, making it the driest place on Earth. The McMurdo Dry Valleys in Antarctica have not seen rain for nearly 2 million years, yet even here, microorganisms survive inside rocks and in the thin layers of liquid water that briefly exist during the short Antarctic summer. Let your thoughts now drift across the oceans to the scattered islands that dot our planet's surface, each one a world unto itself. Islands have long captured human imagination, serving as laboratories of evolution, sanctuaries for unique species, and windows into how life adapts to isolation. There are approximately 180,000 islands on Earth, with an area greater than about 2.5 acres. These range from tiny coral atolls barely rising above the waves to massive landmasses like Greenland, the world's largest island, covering about 836,000 square miles. Islands represent only about 5% of Earth's total land area, yet they harbor a disproportionate share of our planet's biodiversity. The Hawaiian Islands formed as the Pacific Plate moved slowly over a stationary hotspot in Earth's mantle. Magma rising from this hotspot created a chain of volcanic islands, with the oldest and most eroded islands to the northwest and the youngest, including the Big Island of Hawaii, to the southeast. The Big Island is still growing today as Kilauea and Mauna Loa continue to erupt, adding new land to the coastline. Hawaii is one of the most isolated island chains on Earth, located more than 2,000 miles from the nearest continent. This isolation has made Hawaii a showcase for evolution. Species that arrived on the islands, carried by wind, waves, or birds, evolved in isolation for millions of years, producing an extraordinary diversity of unique species found nowhere else on Earth. A single species of finch that arrived millions of years ago eventually evolved into dozens of species of Hawaiian honeycreepers, each adapted to a different food source. The Galapagos Islands, straddling the equator about 600 miles off the coast of Ecuador, are perhaps the most famous laboratory of evolution. It was here that Charles Darwin made observations that would eventually lead to his theory of natural selection. The island's giant tortoises, marine iguanas, and Darwin's finches each demonstrate how species adapt to their environments over generations. Madagascar, the world's fourth-largest island, separated from the African continent about 160 million years ago, and from India about 88 million years ago. This long isolation has produced an extraordinary assemblage of unique species. About 90% of Madagascar's wildlife is found nowhere else on Earth, including all of its lemurs, more than half of its chameleons, and virtually all of its native plants. New Zealand separated from the ancient supercontinent Gondwana about 85 million years ago, before most mammals had evolved. In the absence of mammalian predators, birds evolved to fill ecological niches typically occupied by mammals elsewhere. The kiwi, a flightless bird about the size of a chicken, behaves much like a small mammal, using its long beak to probe for invertebrates in the leaf litter. The now extinct moa, the tallest birds ever known, stood up to 12 feet tall and filled the role of large browsing mammals. Islands are often the first places where species go extinct due to human activities. Because island species often evolved without predators, they may have no fear of humans or introduced animals like rats, cats, and pigs. The dodo of Mauritius, the moa of New Zealand, and countless other island species were driven to extinction within years or decades of human arrival. Today, islands account for more than half of all recorded extinctions. Coral atolls represent a special type of island, formed when coral reefs grow around a volcanic island that then slowly sinks beneath the waves. The coral continues to grow upward, keeping pace with sea level, until eventually only a ring of coral-capped reef remains, encircling a central lagoon. The process was first described by Charles Darwin, and his explanation has been confirmed by drilling through atolls to find the volcanic rock buried far below. The Maldives, a nation of approximately 1,200 coral islands in the Indian Ocean, is the world's lowest-lying country, with an average ground level of only 4 feet above sea level. The highest natural point in the entire country is only about 8 feet above sea level. Rising seas pose an existential threat to the Maldives and other low-lying island nations, many of which may become uninhabitable within this century. Beneath your feet, whether you stand in a forest, a field, or a garden, lies one of Earth's most overlooked wonders: soil. This thin layer of material covering much of our planet's land surface is a complex mixture of minerals, organic matter, water, air, and countless living organisms. Without soil, terrestrial life as we know it could not exist. Soil forms incredibly slowly, typically taking about 500 years to produce just 1 inch of topsoil under natural conditions. The process begins when rocks are broken down by physical and chemical weathering, by the expansion and contraction of freezing and thawing, by the action of wind and water, and by the acids produced by lichens and plant roots. This mineral component is then mixed with organic matter from decaying plants and animals, creating the fertile medium in which plants grow. A single teaspoon of healthy soil contains more living organisms than there are people on Earth. This hidden world includes bacteria, fungi, protists, nematodes, earthworms, and countless other creatures. These soil organisms play essential roles in breaking down organic matter, recycling nutrients, and maintaining soil structure. Without them, dead plants would pile up indefinitely, and nutrients would remain locked away, unavailable to living plants. Earthworms are among the most important engineers of soil ecosystems. Charles Darwin spent decades studying earthworms and wrote an entire book about them, concluding that few other creatures have played such an important role in the history of the world. Earthworms consume organic matter and mineral soil, mixing them in their guts and depositing nutrient-rich castings throughout the soil. They also create burrows that improve drainage and allow air to reach plant roots. Fungi form vast underground networks called mycelia, which can spread across entire forests. A single fungal individual in Oregon's Blue Mountains covers about 2,400 acres and is estimated to be between 2,000 and 8,000 years old. These fungal networks connect trees and other plants, allowing them to share nutrients and chemical signals. Some scientists refer to this underground network as the Wood Wide Web. Different regions of Earth have developed different types of soil, each with its own characteristics and capabilities. The black soils of the Ukrainian steppes and the American Great Plains are among the most fertile on Earth, rich in organic matter from thousands of years of grassland vegetation. These soils can be several feet deep and contain enough nutrients to support intensive agriculture. In contrast, the soils of tropical rainforests are typically thin and poor in nutrients, despite the lush vegetation they support. Most of the nutrients in a tropical forest are locked up in the living vegetation, continuously recycled through rapid decomposition and uptake. When tropical forests are cleared, the thin soils are quickly depleted, often becoming unsuitable for agriculture within a few years. Permafrost, permanently frozen soil found in polar and high mountain regions, covers about a quarter of the northern hemisphere's land surface. This frozen ground can extend hundreds of feet deep and contains vast amounts of organic carbon, accumulated over thousands of years. As the climate warms and permafrost thaws, this carbon is released as carbon dioxide and methane, potentially accelerating climate change in a feedback loop. Soil erosion is one of the most serious environmental challenges facing humanity. Wind and water can remove topsoil far faster than natural processes can replace it, especially when protective vegetation is removed. Some estimates suggest that agricultural land is losing topsoil 10 to 40 times faster than it can be regenerated. At current rates, the world could lose most of its productive topsoil within 60 years. The soil beneath your feet has been forming since the last ice age retreated, thousands of years ago. It contains minerals weathered from ancient rocks, organic matter from countless generations of plants and animals, and living organisms that continue the slow work of building and maintaining this precious resource. Every grain of sand was once part of a larger rock. Every particle of organic matter was once a living thing. The soil is a record of history, a foundation for the future, and a reminder of our connection to the deep processes of the Earth. Deep beneath the surface, Earth's interior heat continues to shape our world. This heat, left over from the planet's formation and continuously generated by radioactive decay, drives the movement of tectonic plates, creates new crust at mid-ocean ridges, and sometimes erupts spectacularly at the surface through volcanoes. There are approximately 1,500 potentially active volcanoes on Earth's surface, with about 50 erupting in any given year. The ring of fire around the Pacific Ocean contains about 75% of these volcanoes, a consequence of the subduction zones where oceanic plates dive beneath continental plates. As the descending plate reaches hot depths, water released from the rock lowers the melting point of the overlying mantle, generating the magma that feeds volcanic eruptions. Mount Vesuvius in Italy famously buried the Roman cities of Pompeii and Herculaneum in 79 AD, preserving them under layers of volcanic ash and pumice for nearly 2,000 years. The sudden burial preserved remarkable details of Roman daily life, from bread left in ovens to the forms of people caught in the disaster. Today, Vesuvius remains one of the most dangerous volcanoes on Earth, with about 3 million people living in its potential impact zone. The most powerful volcanic eruption in recorded history was Mount Tambora in Indonesia in 1815. This massive eruption ejected approximately 36 cubic miles of material into the atmosphere, killing an estimated 71,000 people directly and causing global climate disruption that led to the year without a summer in 1816. Crops failed across the northern hemisphere, leading to the worst famine of the 19th century. Yellowstone National Park sits atop one of the world's largest volcanic systems. A vast magma chamber lies beneath the park, responsible for the geysers, hot springs, and other thermal features that make Yellowstone famous. The Yellowstone supervolcano has produced 3 massive eruptions over the past 2 million years, the most recent about 640,000 years ago. A future eruption on this scale would have catastrophic global consequences, though such an event is not considered imminent. Geysers are among the most dramatic expressions of Earth's internal heat. Old Faithful in Yellowstone erupts approximately every 90 minutes, shooting a column of boiling water up to 180 feet into the air. The eruption occurs when groundwater heated by magma deep below builds up enough pressure to overcome the weight of water above it. After the eruption, the underground chambers refill, and the cycle begins again. Hot springs and geothermal vents support unique ecosystems that thrive on Earth's internal heat. Thermophilic bacteria live in water too hot for most other life, sometimes in temperatures exceeding 200 degrees Fahrenheit. These heat-loving organisms are thought to represent some of the earliest forms of life on Earth and may provide clues about how life could exist on other worlds. Iceland harnesses its abundant geothermal energy for heating and electricity generation. About 90% of Icelandic homes are heated with geothermal hot water, and geothermal power plants provide about 25% of the nation's electricity. The country's position on the Mid-Atlantic Ridge provides an essentially inexhaustible source of heat, making Iceland one of the leaders in renewable energy. The deepest volcanic vents are found on the ocean floor at hydrothermal vents, where superheated water laden with dissolved minerals emerges from cracks in the Earth's crust. The water at these vents can exceed 700 degrees Fahrenheit, but remains liquid due to the extreme pressure. When this hot water meets the cold surrounding seawater, minerals precipitate out, forming towering chimney structures called black smokers. Hydrothermal vents support thriving ecosystems in the complete absence of sunlight, relying instead on chemicals from Earth's interior for energy. Giant tube worms, some over 6 feet long, cluster around the vents, hosting bacteria in their bodies that convert hydrogen sulfide into food. Ghostly white crabs, eyeless shrimp, and strange fish also inhabit these deep-sea oases. The discovery of these ecosystems revolutionized our understanding of where life can exist and expanded the potential for life beyond Earth. As you rest here tonight, the Earth continues its eternal cycles, the rhythms that have governed life since the earliest times. The tilt of our planet's axis creates the seasons, the orbit around the sun marks the years, and the rotation gives us the comforting alternation of day and night. Earth's axis is tilted at approximately 23.4 degrees relative to its orbital plane around the sun. This seemingly modest angle has profound consequences for life on our planet. When the northern hemisphere is tilted toward the sun, it experiences summer, with longer days and more direct sunlight. 6 months later, the southern hemisphere takes its turn, while the north experiences winter's cold embrace. At the summer solstice, the longest day of the year, the sun reaches its highest point in the sky. In the northern hemisphere, this occurs around June 21st, when locations above the Arctic Circle experience the midnight sun, with 24 hours of continuous daylight. At the same time, locations below the Antarctic Circle experience polar night, with the sun never rising above the horizon. The equinoxes, occurring around March 20th and September 22nd, mark the moments when day and night are approximately equal in length across the entire globe. At these times, the sun rises due east and sets due west, and the terminator, the line separating day from night, runs directly from pole to pole. The changing seasons drive migrations that span continents. Arctic terns make the longest migration of any animal, traveling from Arctic breeding grounds to Antarctic feeding grounds and back again each year, a round trip of about 44,000 miles. These small birds experience 2 summers each year and more daylight than any other creature on the planet. Monarch butterflies undertake one of the most remarkable migrations in the insect world, traveling up to 3,000 miles from Canada and the United States to their overwintering grounds in the mountains of central Mexico. The butterflies that arrive in Mexico are the great-great-grandchildren of those that left the previous spring. Somehow, butterflies that have never made the journey before know exactly where to go. The seasons also drive the great cycles of plant life. In temperate forests, trees prepare for winter by withdrawing nutrients from their leaves, creating the spectacular colors of autumn. The green chlorophyll breaks down, revealing the yellow and orange pigments that were present all along, while some trees produce red pigments that may help protect the leaves as they shut down. The monsoons are among the most dramatic seasonal events on Earth. The South Asian monsoon brings about 70% of India's annual rainfall during the summer months, as moisture-laden winds sweep in from the Indian Ocean. About 1 billion people depend on the monsoon rains for their water supply and agricultural needs. A weak monsoon can bring drought and famine, while an excessive monsoon can cause catastrophic flooding. The Earth's orbit around the Sun is not perfectly circular, but slightly elliptical. Currently, Earth is closest to the Sun in early January and farthest in early July. This might seem counterintuitive, since January is winter in the northern hemisphere, but the effect of the orbital distance is small compared to the effect of the axial tilt. The southern hemisphere does experience slightly more intense summers due to being tilted toward the Sun when Earth is closest. Over long timescales, the shape of Earth's orbit, the tilt of its axis, and the direction its axis points all vary in predictable cycles. These Milankovitch cycles, named after the Serbian scientist who calculated them, operate over periods of thousands to hundreds of thousands of years. They are thought to be the primary driver of the ice ages that have periodically gripped our planet, subtly changing the distribution of sunlight in ways that allow ice sheets to grow or retreat. Gravity, that most familiar yet mysterious force, holds you gently in your bed tonight. It keeps the oceans in their basins, the atmosphere wrapped around the planet, and Earth in its orbit around the Sun. Without gravity, our world would fly apart, and life as we know it could not exist. Earth's gravity accelerates objects at the surface at about 9.8 meters per second squared. This means that a falling object gains about 22 miles per hour in speed for every second it falls, ignoring air resistance. This gentle but inexorable pull has shaped every aspect of our planet, from the spherical form of Earth itself to the flow of water from mountains to sea. Gravity is not perfectly uniform across Earth's surface. Because Earth is not a perfect sphere, but slightly flattened at the poles and bulging at the equator, gravity is slightly stronger at the poles than at the equator. Local variations in rock density also affect gravity, allowing geologists to map underground structures by measuring tiny variations in gravitational pull. A dense deposit of iron ore, for example, will produce a slightly stronger gravitational pull than surrounding rock. The moon's gravity creates the tides that wash our shores twice each day. As the moon orbits Earth, its gravitational pull creates a bulge in the ocean on the side of Earth facing the moon. A second bulge forms on the opposite side of Earth, where the moon's gravity is weakest and water is left behind as Earth is pulled toward the moon. As Earth rotates beneath these bulges, coastal areas experience the rhythmic rise and fall of the tides. The highest tides on Earth occur in the Bay of Fundy, between Nova Scotia and New Brunswick in Canada. Here, the shape of the bay amplifies the tidal range to about 53 feet, the height of a 5-story building. Twice each day, 100 billion tons of water flow in and out of the bay, more water than the combined flow of all the world's freshwater rivers. Gravity drives the water cycle, pulling rain from clouds to Earth and drawing rivers downhill to the sea. It causes landslides and avalanches, shapes the slopes of mountains, and determines how tall trees can grow. The tallest trees on Earth, the coast redwoods of California, grow to about 380 feet, near the theoretical maximum height that water can be lifted against gravity through a tree's vascular system. The gravitational interaction between Earth and Moon has profound consequences that play out over geological time. Tidal friction is gradually slowing Earth's rotation, making each day slightly longer than the one before. At the same time, the Moon is slowly spiraling away from Earth. Billions of years ago, the Moon was much closer, the days were much shorter, and the tides were far more extreme than today. Gravity binds Earth and the other planets to the Sun, and the Sun to the Milky Way galaxy. The Sun orbits the center of the galaxy at about 500,000 miles per hour, taking about 230 million years to complete one orbit. In the 4.5 billion years since Earth formed, our planet has completed only about 20 orbits around the galactic center. On the largest scales, gravity shapes the structure of the entire universe. It draws matter together into galaxies, galaxies into clusters, and clusters into vast cosmic filaments spanning hundreds of millions of light years. The largest structures in the universe, the great walls and filaments of galaxies, are all held together and shaped by gravity, the same force that keeps your body pressed gently against your bed. If you were to look out your window on a clear, dark night, you would see the same stars that have guided travelers and inspired dreamers for thousands of years. The night sky is a window to the universe, connecting us to distant worlds and times long past. On a truly dark night, far from city lights, the naked eye can see approximately 2,500 stars. With the addition of a small telescope, millions more come into view. Each of those points of light is a distant sun, many larger and brighter than our own, scattered across the vast reaches of space. The light from the nearest star beyond the Sun, Proxima Centauri, takes about 4.25 years to reach Earth. When you look at that star, you're seeing it as it was 4 years ago. The light from Sirius, the brightest star in our sky, has traveled about 8.5 years. The light from Polaris, the North Star, has been traveling for about 400 years, meaning it left that star around the time Galileo was pointing his telescope at the heavens. The Milky Way, that pale band of light stretching across the sky, is actually the combined light of billions of stars in the disk of our galaxy. When you look at the Milky Way, you are looking into the heart of our galactic home, toward the dense star clouds of the galactic center. Every star you can see with the naked eye belongs to the Milky Way. The distant galaxies are too faint to see without optical aid. The Andromeda Galaxy is the most distant object visible to the naked eye, a faint smudge of light about 2.5 million light-years away. The light reaching your eyes tonight began its journey when our ancestors were first learning to make stone tools. Andromeda contains approximately 1 trillion stars, about twice as many as the Milky Way, and is moving toward us at about 70 miles per second. Meteors, commonly called shooting stars, are not stars at all but tiny pieces of cosmic debris burning up as they enter Earth's atmosphere. Most meteors are produced by particles smaller than a grain of sand, traveling at speeds of 20 to 40 miles per second. The friction with the atmosphere heats the particle and the surrounding air to incandescence, producing the brief streak of light we see. Meteor showers occur when Earth passes through trails of debris left by comets. The Perseid meteor shower in August is caused by debris from Comet Swift-Tuttle, while the Leonid shower in November comes from Comet Tempel-Tuttle. During peak activity, observers in dark locations might see dozens or even hundreds of meteors per hour, all appearing to radiate from a single point in the sky. The planets, those wandering stars known to ancient observers, follow paths across the sky quite different from the fixed stars. Because the planets orbit the Sun like Earth does, they appear to move slowly against the background of stars, sometimes even appearing to reverse direction in their characteristic retrograde motion. Venus, the brightest planet, can outshine everything in the sky except the Sun and Moon. The Moon, our closest celestial neighbor, dominates the night sky when present. Its surface, scarred by billions of years of impacts, is visible in remarkable detail even with the naked eye. The dark areas, called maria, are ancient lava flows that filled large impact basins. The bright areas are the original crust, heavily cratered by the bombardment that shaped the early solar system. Light pollution from cities has hidden the night sky from much of humanity. About 80% of North Americans and 60% of Europeans can no longer see the Milky Way from their homes. This loss of darkness affects not only our view of the cosmos, but also the behavior of countless species of animals that depend on natural cycles of light and dark. As we approach the end of our journey, let us contemplate the remarkable interconnectedness of Earth's systems. Our planet is not a collection of separate components, but a single, integrated system where everything is connected to everything else, often in ways we are only beginning to understand. The atmosphere, oceans, land, and living things are all linked through cycles of matter and energy that span the globe. Carbon atoms cycle between air, water, rock, and living things, spending years in plants, centuries in soil, and millions of years locked in limestone. Water evaporates from tropical oceans, falls as snow on distant mountains, and eventually returns to the sea through rivers or groundwater. Nitrogen fixed by bacteria in the roots of plants may end up in the body of an animal on the other side of the world. Dust blown from the Sahara Desert fertilizes the Amazon rainforest, carrying phosphorus that would otherwise be in short supply. About 27 million tons of Saharan dust settles on the Amazon basin each year, providing essential nutrients that sustain the world's largest rainforest. When the Sahara was green during past climate cycles, this nutrient source was cut off, potentially affecting the rainforest thousands of miles away. Ocean currents connect the world's seas in a global conveyor belt that takes about 1,000 years to complete. Water that sinks in the North Atlantic may not return to the surface until it reaches the Indian or Pacific Oceans centuries later. This global circulation distributes heat around the planet, moderating temperatures and affecting weather patterns far from the ocean. The warming of the tropical Pacific Ocean during El Niño events affects weather across the entire globe. Droughts strike Australia and Indonesia, while floods hit Peru. California receives more rain, while the Amazon becomes drier. Coral reefs bleach, fish populations shift, and agricultural yields change on every continent. A single climate pattern in one part of the ocean ripples across the entire planet. Living things have transformed Earth in countless ways over billions of years. Photosynthetic organisms created the oxygen in our atmosphere, changing the chemistry of the air, ocean, and rocks. Plants colonized the land, creating soil, altering weathering patterns, and completely transforming terrestrial landscapes. Animals evolved to eat plants, and predators evolved to eat them, creating the complex food webs that sustain modern ecosystems. Humans have become the dominant force shaping the Earth's surface. We have transformed about 3/4 of the ice-free land surface, changed the composition of the atmosphere, acidified the oceans, and moved more rock and sediment than all natural processes combined. Our actions affect every corner of the globe, from the deepest ocean trenches to the upper atmosphere. Yet Earth has proven remarkably resilient over its 4.5 billion year history. The planet has survived massive asteroid impacts, volcanic catastrophes, and ice ages that covered much of its surface. Life has persisted through mass extinctions that wiped out most species, rebounding each time to fill the world with new forms. The Earth system has maintained conditions suitable for life for billions of years, through feedback mechanisms we are still working to understand. And now, dear listener, as these facts about our remarkable planet settle into your mind like sediment drifting to the ocean floor, allow yourself to sink deeper into rest. Earth continues its ancient dance through space, rotating steadily on its axis, orbiting faithfully around the sun, drifting with the Milky Way through the cosmos. You are part of this planet, made from its elements, breathing its air, drinking its water. The iron in your blood was forged in the heart of an ancient star. The calcium in your bones was once dissolved in primordial seas. The carbon in your cells has cycled through countless other organisms over billions of years. You are, in a very real sense, the Earth become aware of itself. Rest now, carried on the surface of this spinning blue marble through the endless night of space. Let the gentle rhythm of your breathing match the patient pulse of the planet. The mountains will still stand guard in the morning. The oceans will continue their eternal tides. The stars will wheel overhead as they have for billions of years, silent witnesses to the story of Earth. Sleep peacefully, knowing you are home. Sleep deeply, cradled by gravity, sheltered by the atmosphere, protected by the magnetic field that has guarded life for billions of years. Tomorrow the sun will rise again, as it has done 4.5 billion times before, painting the sky in colors born of the scattering of light through our precious atmosphere. The Earth holds you safe tonight, as it has held countless generations before you. The same gravity that keeps the oceans in their basins and the atmosphere wrapped around the planet holds you gently in your bed. The same physical laws that govern the motion of planets and stars govern the beating of your heart and the rhythm of your breathing. Let go of the day's concerns. Let go of tomorrow's worries. In this moment, there is only you and the ancient Earth, two partners in an endless dance that began when the first dust grains began to stick together in the solar nebula 4.5 billion years ago. The rivers will continue to flow to the sea. The forests will continue their slow growth toward the sky. The tectonic plates will continue their patient drift across the face of the globe, and you will continue to rest, supported by this magnificent planet that has nurtured life for so long. Feel the weight of your body sinking deeper into your bed. Feel your breath slowing, your thoughts quieting, your mind drifting toward sleep. The Earth turns beneath you, carrying you through the darkness toward the dawn. But that is hours away. For now, there is only rest, only peace, only the quiet embrace of night. The same stars that shine through your window tonight have shone on every generation of humans who ever lived. They shone on your ancestors, on the first humans who walked out of Africa, on the dinosaurs, on the earliest life in the ancient seas. They will shine on for billions of years to come, long after the concerns of this day have been forgotten. You are connected to all of it, to the deep past and the distant future, to the smallest bacteria and the largest galaxies. You are made of the same atoms that have been cycling through the Earth for billions of years, the same atoms that will continue to cycle long after you are gone. In this sense, you are eternal, part of the great unfolding story of the cosmos. Until the morning comes, rest well. The Earth continues its journey through space, carrying you along, keeping you safe, providing everything you need. Sleep now and dream of gentle things, of mountains and oceans, of clouds and stars, of the endless wonders of this beautiful blue planet we call home. The night is deep and peaceful. The Earth holds you close, all is well. Good night.